Hello, so today I'm going to explain about quantum physics sequence. Let's start with the discovery of electron. This is J.J. Thomson. He discovered electron in 1897. He found out that atoms were not the most basic form of matter. It is electron. Cathode rays could be reflected or bent by magnetic or electric fields. It indicates that cathode rays consist of charged particles. He then detected that the particles was coming out from the negatively charged or called cathode to positively charged or anode. Next up in the quantum physics sequence is blackbody radiation. What is a blackbody radiation? A blackbody is an object or system which absorbs all electromagnetic radiation falling upon it without reflecting or transmitting any. Its radiation is a thermal radiation that emits in continuous spectrum according to the temperature. The discovery of electron could help in explaining blackbody radiation. Although at the end of 19th century, physicists were unable to explain the reason why spectrum of blackbody radiation was significantly at higher frequencies than the predicted theories. Next up, Max Planck suggested the quantum hypothesis in the 1900s. He came up with the idea when attempting to explain the unsolved blackbody radiation. He hypothesized that light energy can only be emitted and absorbed in the discrete bundles called quanta. Moreover, he also said in his book, it is necessary to interpret the total energy of a blackbody radiation not as a continuous infinitely divisible quantity, but as a discrete quantity composed of an integral number of infinite equal parts. Next is photon theory of light. It explained that both light and matter consist of tiny particles which have wave-like properties associated with them. Light is composed of photons and matter is composed of electrons, protons, and neutrons. Next one is the photoelectric effect. It explained that electrically charged particles are released from or within a material when it absorbs electromagnetic radiation. The puzzling questions regarding the nature of light and the particles versus wave-like behaviors were finally resolved by Albert Einstein in the 1905, thanks to Planck's hypothesis that electromagnetic wave may behave like charged particles. Continuing photon and photoelectric effect. Photons are always in motion and have a constant speed of light. Energy of a photon can be determined using the photoelectric effect. Photons have zero mass. Next is Compton Effect. It is the term used for an unusual result observed when X-rays are scattered on some materials. Prediction shows that when X-rays were scattered, the wavelength of the scattered radiation is expected to be the same as the wavelength of the incident radiation, while observation shows that when X-rays are scattered, it will have different wavelengths from the incident X-rays. This unusual result becomes once again an unexplainable phenomenon. Though it has been studied experimentally by Arthur H. Compton, Compton used Einstein's idea of light. The Compton effect gave a convincing argument that electromagnetic waves can indeed behave like a stream of photons. The wave versus particle behavior has been a debate for a long time. Now, it is time to take a conclusion on how to deal with the duality. First up, what is duality? Duality is an instance of opposition or contrast between two concepts. Duality is not a boundary. It is a way to analyze two different concepts in one thing. First up is complementary principle. It was suggested by Niels Bohr. Since these two models are mutually exclusive, they cannot be used simultaneously. Light and electrons possess the properties of both particles and waves, but only until they are observed, at which point they behave as if they are either one or the other, depending upon the experiment. Other ways to utilize the duality is by de Broglie wave nature of matter. If radiation has both particles and wave properties, then nature would be symmetric. If matter also had both particles and wave properties, it would be also symmetric. If what we once thought of as a radiation is also a particle, then matter may also be a wave. By using Bohr's complementary principle and de Broglie's wave nature of matter, wave and particle finally met their middle way. Aside from wave-particle duality, Bohr also made a model for properties of atomic electrons. Before 1913, an atom was thought of as consisting of a tiny positively charged heavy core called a nucleus surrounded by light planetary negative electrons revolving in circular orbits or arbitrary radius. Though Bohr amended that. In the Bohr model, electrons travel in the defined circular orbits around the nucleus. The orbits are labeled by an integer, the quantum number n. In addition to that, there are also de Broglie's hypotheses. De Broglie says that all matter has both particles and wave nature, but this is only a hypothesis because there was no evidence for it when it was proposed. Though de Broglie's hypothesis was the next step in quantum theory and may open more discoveries in modern physics.